How do you manage wavefront scatter and thermal drift across an off-axis parabolic geometry? It requires balancing the dominant error mechanisms of your substrate against application constraints. For prototyping and broadband infrared spectroscopy, aluminum and electroless nickel-plated substrates offer highly predictable performance for the cost. Machined via single-point diamond turning, they serve as a practical baseline for FTIR instruments. When migrating to visible and UV wavelengths, where micro-roughness dominates scatter, fused silica and optical glasses are often selected. Processed via deterministic grinding and pitch polishing, glass substrates minimize periodic surface structures to support low scatter, high contrast imaging and microscopy. If localized thermal gradients risk inducing figure error, low expansion materials like Zerodur and ULE minimize distortion. With a coefficient of thermal expansion near zero, these substrates maintain surface figures down to lambda over 40 PV under high thermal flux or intense laser exposure. Where the limiting design constraints are structural dynamics and mass, silicon carbide becomes a viable alternative. Offering exceptional specific stiffness and hardness, silicon carbide structures can be lightweighted by over 80% while retaining high resonant frequencies, making them well-suited for high-speed industrial scanning mirrors and rugged field metrology. Ultimately, substrate selection is a multivariable trade space. Your unique combination of budget, fabrication limits, and thermal environments will dictate the optimal material choice. Avantier, empowering optical innovations.